First of all, thank you very much for the invitation and the introduction. This is a pleasure to present the latest development of our light source that is completely brand new and fourth generation synchrotron, Sirius. So I'll give you, sorry. So I'm going to present the new light source in Brazil, and in particular the two beamlines that will be dedicated to small angle scattering. We are still in commissioning phase. However, we do accept users as well. And so the beamline I'm in charge of and I've been leading the design, construction, and now commissioning is called the Caterete beamline. And it's dedicated to coherent scattering, imaging in particular, XPCS and ultra small angle scattering. The idea is to make the most of the coherence properties of these new light sources. And so here is a picture of the experimental Hutch that you see on the right and the tunnel with the detector inside. So CNEPEM, that is the National Center for Research in Energy and Materials. We are in Campinas in São Paulo state. This is the aerial view of our campus. So you see on the left side, you can see the synchrotron Sirius with these 6 long beamlines over here. Over here, LNBO is a structural biology platform. Over here, LN-nano is electron microscopy. And LNBR is a lab dedicated to bioethanol research. Over here, you can see this is the old building that was hosting the previous synchrotron, that is as well the LNLS, that is the National Lab light source. And this one was dismounted a few years back, about 2 years back. It was completely turned off. So you can see this was a second generation source. It was working beautifully. You have the ring over here, so the booster in there. The linha was actually underground, and you had all those beamlines. So the SAXS beamlines, we used to have 2 SAXS beamlines and about 20 beamlines, if I'm not mistaken. So now it's in dismantling. The old beamlines have disappeared, and the next step, I think, is going to be to remove the ring. So Sirius is the latest generation machine, 5-bend-achromat lattice. This is the view from the top. You see all those 6 beamlines, long beamlines, which are actually the first beamlines being built. We are operating at 3 JAV. Circumference is about a bit more than 500 meters, and the emittance a bit less than 250 picometer hard. This value will decrease along the time when undulators will be inserted into the machine. It's equipped with super band as well, 3.2 Tesla, which have a critical energy of 19 kiloelectron volts. So this is a schematic of a synchrotron, the LINAC. So the LINAC started operation in 2018, 2019. It was purchased from Shanghai in China. You have the booster. The booster, that's the storage ring, the connection between the booster and the storage ring. Over here is the storage ring. So what you see, we have a single tunnel that was built similarly at the same time as the floor of the synchrotron. So this is a single block. You have the storage ring over here on the left side. These are for the front end for the beamlines. And on the right side of the tunnel, you have the booster. So the booster is over here. These are the super vents, so high permanent magnets, the cavities, and the front ends that all beamlines have more or less the same designs. So what you see in red on this schematic are the beamlines which are operational today or in early commissioning phase. So you have Carnaúba. Carnaúba beamline is the longest beamline. It's about 140 meters. It's the nanopro beamline. It's actually equipped with 2 end stations, one for micro beam, let's say, a bit less. And they will have a second end station that they are building, actually. That is going to be the nanoprobe itself, going down to 30 nanometers. So over there, they're going to do tycho, they're going to do nano diffraction, fluorescence, typical experiment. Caterete, so we are here in the second long section. I'll come back in more details afterwards. EMA is the high pressure beamline facility, so they can do EXAF, diffraction as well. Bragg CDI is one of their aim. And they have all equipments related to high pressure, mainly using diamond anvil cells, and as well high temperature with lasers that they can be several thousand kelvins. There is Manaka, that was the very first beamline taking beam. Manaka is the protein crystallography beamline. For now, the first end station is inside the hole, and there is a plan for extending it in this long session to have nanobeam. Meneau is the tomography beamline, cone beam beamline. IP is the latest undulator beamline. This is inelastic X-ray scattering beamline. So they got light, the first light in December, I think, and they are now in the active commissioning phase. And Imbuya is the latest one that got beam. This is the infrared beamline. It's part of it has been transferred from the old ring LNLS. And they received their first light, infrared light, about 2 weeks ago. And here in blue, you have the other beamlines, which are either in construction, like Panera is the power the diffraction, Sapucaia is the small angle scattering beamline. So they have their optical Hutches and the experimental one, I think, and they received the tunnel, and they are basically mounting all equipments, what is the quick EXAFs. And in grid, these beamlines do not have fundings. So this is the status. So today we are operating at 100 milliamps. So this is the view of the Caterete beamline, but briefly before, I'll say a few words about the Sapucaia beamline. So all beamlines are named after either Brazilian animals or trees. So Caterete is it's like a big oak, and Sapucaia is a lovely tree, fairly big, with lovely pink flowers. So this beamline is, the project is led by Leandro Barbosa. He's affiliated with the University of São Paulo as well, he's professor there. The beamline is going really to be the beamline dedicated to small angle scattering, so really serving the whole SAXS community that is a quite strong community in Brazil. In fact, the very first beamline that was, if I'm not mistaken, the very first beamline built at the old ring was a small angle scattering. I think it was Professor Aldo Krajowicz that was part of this project. And so Sapucaia is going to be mainly, so the community is kind of divided in two. You have half would be about structural biology. So there will be a strong focus on structural biology, and the rest material science. So the beamline is going to be undulated beamline using the KEMA undulator. It's going to operate in the 5 to 18 kiloelectron volts. They're going to have a DCM, so double crystal monochromator. These monochromators have been developed in-house at the LNLS. And they are already, this DCM already equipped the EMA and the Manaka beamline. So it's kind of improved, and they're going to have an improved version of this monochromator. They expect to have a beam of about 200 by 200 micron squared, and close to 10 to the 14 photons per second, reaching Q values close to 10 to the -4 inverse angstroms. So this is a schematic of the beamline. So they have the optical Hutch. It's already mounted. This optical Hutch is the one that most of the beamlines are sharing. It's a design that was done at the early beginning of the project, and it's been the same one being built by Brazilian companies and being put for all beamlines. And the experimental Hutch is inspired on ours. And then they have a tunnel as well that will enable them to adjust the sample to detect the distance up to 10 meters. This tunnel is based on the one that we have, but in fact, that is a modified version of the one existing at ID2 at ESRF. Regarding sample environments, so structural biology, so they are already developing a liquid flow cell. However, they would like to purchase the Arinax automatic sample changer robot. This will depend on fundings, but what they have already equipments that we had at the LNLS, the old ring, they have HPLC that can be coupled with Sparkleland automatic sample loading. We have stop flows. There was a project that was developed a few years back called LabWeb that enables remote operation for sample, like called solid samples, powders, or self-standing samples that users could ship, and then they could measure remotely. Over here is missing. We have as well, like I guess most of the SAXS beamlines, we have linker stages, both heating and stretching devices. So this is about Sapucaia. Regarding Caterete, so the beamline has been taking the very first light in July 2020. So that was like kind of the beginning of the pandemic. So that's when we started our commissioning. So obviously things have not been as smooth as we have expected. So limited resources. However, we managed. So we are situated over here on the second long beam line. It's a 120 meter long beam line. And really the objective over here is to make the most of the current properties of the beam. So the main objective is to perform plane wave CDI. The beamline optics and design has been optimized for plane wave CDI, but as well, of course, doing typography. Borax CDI is going to come in the latest stage. And there is a big research field that has to be developed now with X-ray photon correlation spectroscopy. Considering the flux that we have, this is well-known hungry photon techniques that will benefit of it. And the design we have, of course, and the flux we can do time resolved, small angle scattering, and in particular, this is the big difference with the Sapucaia beamline, is to perform ultra small angle scattering. So, as I said, these are the three main technical scientific fields that we aim to develop. Plane wave CDI, so I guess everybody is aware, but basically you have a current wave front. You shine, you over illuminate your sample, and you collect the scattering pattern in the far field. And by doing this, then you can apply phase retrieval algorithm and reconstruct your sample in 2 dimensions. And if you do tomography measurements, you rotate your sample, then you can obtain 3-dimensional structures. So this is an example that was collected at ID10. This is a sugarcane bagasse. And the idea over here is to understand the pore network inside these samples, which have been treated or not treated, in order to produce then ethanol. So one big objective is indeed imaging. Second one is X-ray photon correlation spectroscopy. We have a detector as of today that enables us to work up to 2 kilohertz. And finally, ultra small angle scattering. So you have over here collagen and over here latex particles, just as examples. So we operate in actually in the 3 to 24 keV. Measured photon flux, we have 710 to the 11 at 10 keV today with 100 milliamps. So we are matching the simulations that we had. We are working, we have the tunnel that can enable us to up to 30 meters sample to detector. And we have a detector that we'll describe a little bit later that has been built in-house as well by Detector Group in collaboration with a company called Pitec here in Campinas. It's a Medivix-based detector, so that's what you see in the corner over here. So 55 micron pixels and 3000 by 3000 pixels. So the idea regarding imaging, but not only imaging, is really to be able to image large specimens on different length scales. So for the biology, basically a karyotic cell. So basically the idea is to be able to image as a whole, a complete cell. And as the imaging techniques are quantitative, then you can go and retrieve and understand what's inside. So the nucleus, how a nucleus, organelles, and all those components can be affected depending on disease, treatments, or modification that you may apply. And similarly, in the material science, this is an example over here that you see of a free cracking catalyst. The idea is this type of catalysts are spanning over many length scales from the nanometer up to a few tenths of microns. So in this case, this is made of alumina, silica, zeolites, and mesoporous materials. And you really want to have this 3D information in order to understand how networks, how in situ or inoperable conditions, these networks, mass transport phenomena are evolving during reactions. And so for doing this, as I showed, we have this sample to detector distance. And the beam, depending on the energy, can be so fully coherent. has a different size. So on this graph, what you see is maximum beam sample size that you could image using plane wave CDI, and the resolution you would obtain depending on the energy you would use and where you would put your sample to detector distance. So basically over here, the limits would be due to the beam size. So if you go to low energy, this is where the coherent beam is the largest. So potentially where you can measure the largest specimens. And if you decrease the energy, the beam size is going to decrease. And so this is the balance between beam size and pixel resolution. I must say that if you want to explore larger specimens, you can always apply the tychography methods, where you would perform raster scannings, 2D scannings, and then assembling everything into a three-dimensional object. So this is the layout of the beamline. So we are equipped with chemoundulators for now. All the optical elements are sidebands. So we have the first mirror, that is the vertical focusing mirror. All the optical elements are cryo-cooled as well. Then we have the 4cm and the horizontal focusing mirror. The important thing is the 4cm can be translated horizontally and let the pink beam go through. So because the 4cm enables you as well to have fixed exits. So if we translate by a few millimeters the crystals, then we can work with pink beam. It's actually dramatically important in our case because we unfortunately suffered of damage of the 4cm because of the beam. It's actually not exactly clear what really happened, but in any case, so the 4cm is in, the crystals are going to be replaced. So for now, we are operating only with pink beam. So then you have your samples and then detector and sample to detect the distance. It's planned from beginning, we'll have an upgrade of undulator. The idea would be to use delta undulators. So this is still under studies. The main advantage of delta undulators is that you can tune the polarization. So this is nice for magnetic studies, but as well because we have everything sidebands. To work at low energies, you have to have a vertical polarization. So this is an upgrade that is foreseen in a few years' time. And here you have an overview of the beamline. So experimental Hutch with the vacuum tunnel and the Medipix detector that I was mentioning just before. So this detector is inside the tunnel. So that's the main difference with the ID2 tunnel. Our detector is in vacuum, so we don't have this big box. And it's composed of 4, in fact, independent Medipix detector, and then you reconstruct the full image. What you see over here, I have bigger pictures afterwards, is you can see the stripes of chips over here, and they have been all mounted with 90 degrees rotations, enabling to not have any gaps and information all over the space. And the experimental station is over here. That's where you would put your sample, and we can do diffraction as well using the wax detector. So that's a detector that we bought from the previous Synchrotron. So just a slide, just to show very briefly, but this has been published in conference proceedings. All the mirrors and monochromators have been built in-house by the engineering team of CNEPEM and LNLS. So except the mirrors, in our case, that came from GTEC and the crystals from a German company, all the mechanics have been developed over here. So all optical elements are sharing this granite base, where you have levelers with 3 degrees of freedom, and then you have fine translations that you have with those 2 pieces of granite that can slide one above the other one. So you have X and Y. And inside, you have a system all made with flexures hosting the crystals or the mirrors. In this case, this is our vertical focusing mirror. It's 20 centimeters long. And the cooling system over here that is all cooled via gold braid, a specific one. So it's an indirect cooling. So it's not liquid nitrogen flowing, it's really indirect cooling, which enables us to have all optical elements at cryo temperatures. This is the latest measurements of the beam. So basically what you have on the left is a simulation at 10 keV of the beam and the beam size expected. So this is fully coherent beam. And on the right, that's what we measured at the sample position. What you can see is that the horizontal size is well matching the simulations, while there is a slight discrepancy in the vertical direction. There are several factors that could explain this discrepancy. First, we are having over here a ping beam measurement. So it's a 1% bandwidth Well, here it's fully monochromatic, but as well, we're still suffering a bit of beam instabilities due to the machine. It's a bit more complex. There are instabilities from the machines, but as well temperatures, external temperatures. As well, nominal emittance of the machine has not been exactly reached yet, and the fast orbit feedback has not been implemented. So this is going to come next semester, I believe. So this could explain these slight discrepancies. The measured flux, 10 keV, Coherent beam, 710 to the 11 photon per second for 100 milliamps operation. So that's the operation that we are having today. And what you see on this graph as well in blue are the measurements of the focal size at the sample position, depending on the opening, the apertures of the slits. So you clearly see the dip over here that the beam is going to completely defocus or diffraction limited over here. So to summarize, we have a beam in the 30 to 55 microns size, depending on the energy. So today we are, because of the pink beam, and we have to eliminate the harmonics, we are only operating at 3.8 keV or 10 keV. So we have a beam of about 35 microns, 40 microns squared, and divergence below a few microradians. So here what you see is the beam size as function of energy, and this is well matching those simulations. So this is what we have available today for the beamline. So I'm going to show you over here just a word about the tunnel. So it's been built by AVS in Spain. Basically, the idea over here was for funding reasons and manpower reasons, we could not develop such a project in-house just for 1-2 beamlines. So it's been decided strategically to purchase from AVS, benefiting of all the developments that people from USAXS, particularly Narayan, did. And so this is very similar. And basically what you see over here, if I summarize, this is a measurement of the beam movement drift along the distance inside the tunnel. So this was measured with a YAG and a small CCD camera. And this is all summarized over here, the disk of confusion. We have displacement less than 300 microns. So we are talking about 5-6 pixels on the detector, which can easily be corrected, especially that this is highly reproducible. So basically all these fluctuations are more or less due to the fact that we have fit on the floor, and that's the oscillation that you see, but nothing truly important. It takes about 10 hours to pump. We have 2 big pumps. And this is the detector. So you have a closer look at the detector. So you see over here, this is a stripe of 6 256 pixel chips. So you have 6 of them. And then you have 6 of these chips assembled. So this detector is called the 135, so the pi mega detector. And in our case, which is the very first detector that was developed by the company and the Detector group, so we have the very first prototype. This is the largest pixel detector based on Medipix that has been built. And so you see we have the 4 of them. And then the 4 modules, so they are gapless, they are mounted in the tile, so they are not parallel. They are all mounted in the tile geometry in order to remove all gaps to the maximum. So this detector is perfectly suited for working at large sample to detector distance, while if you were very close, then you would lose a lot of pixels because of the geometry. So this is a schematic that you see. The detector can work in 12 and 24 bits. So far we went to 1 kilohertz, and soon we should be able to go to 2 kilohertz frame rate. In fact, we have not explored this yet, but this frame rate could be increased as well by working, I think, in 6 or 2 bits. So there is room for improvement as well. So this is an image of raw data. So these are latex nanoparticles. And what you see over here is the raw data as they come when you do your measurements. So you clearly see those 4 modules over here, and everything is rotated by 90 degrees. So the very first thing that one has to do, but this is obviously will be transparent to the users, is to apply geometrical corrections to reconstruct this full image into a full, complete image that we are more used to. So this is a fairly large beam stop that we are still using nowadays, and you can clearly see all this. These are 1.2 microns, a bit more than 1 micron size latex particles. That's a schematic of the experimental station. So we have the sample over here, this wax detector, and then over here the tunnel. So this is a view of the experimental Hutch. as of today. So we are using this type of mounting, which are highly reproducible. They've been developed mainly for the imaging experiment, where we will mount silicon nitride membranes over here. But obviously, you can mount any samples you wish and put capillaries. Over here as well, we have positioning two mirrors, which are quite useful for the commissioning phase to characterize the stages, displacement, and drift. So because we can use interferometry. This frame, I will talk about it a bit later, but this is holding the cryo system. And over here would be the sample, and this is the entrance to the tunnel. So this is a closer view. We don't use this gold system. This gold system has been used for characterization of the stages, characterizing the wobble, the displacement that we have in all the different stages. So this is a better view of the system. So we have here Arinax optical microscope with a hole inside and a capillary, so we can work with differential pumping and no windows. So you see basically your sample along the beam. The sample would be positioned over here. And the sample is mounted on, we have an hexapod with an air-bearing stage. So the air-bearing stage is to perform the tomography experiment. And on top of it, we have large piezo stages with large coarse movement, all equipped with a slip ring system that we've been developing ourselves, which enables not to damage in any way the movement of the air bearing. And so the advantage of this is you don't have any wires, cables going around. And if we want to do tychography, over here we would place some smaragd stages. We can mount on this frame. It's an optical frame that is made of titanium that has been developed for hosting interferometry system if needed. The main thing that we've been developing, that was one of the very first requirements, was a cryo system, because, well, as everybody knows, radiation damage is an issue, is a big issue. And so that was the very first thing that we are developing, and it's successfully working. So basically, that's the top view. From here, you have the sample, the beam coming across the optical microscope. That's the sample stage. And here we are using Oxford cryo cooling system. Basically, you have inside helium flow at liquid nitrogen temperature or even below, and concentric coaxially, you have a nitrogen flow to avoid freezing. This whole system is mounting on this frame over here that enables to completely dump all instabilities that would be induced by the cryo system itself, because it has a piston inside. The advantage over here is we are using helium gas. We don't need we don't need liquid helium, which would have enormous cost. So this system has been built in such a way that all vibrations are dumped. And what you see here is it's a simple acrylic box that we built, which enables us to control the humidity. And we are working at humidity levels below 2%, which avoids any ice formation. And it shows to be successfully working. So this is a Siemens star to the Tycho image that so we have the Siemens star as a sample. You measure it in Tycho mode. So you basically do raster scan. So we were working at 4 keV. So that's the ping beam. We had a pinhole of 5 microns, and we were making steps of 1.25 microns. You do a 2D image, you reconstruct, and this is the Siemens star that you can reconstruct at room temperature. And then we cool down the Siemens star, and this is the result that we get at 80K. And basically, I don't have over here, but the resolution analysis shows that it's absolutely perfectly stable, and no instabilities are induced, neither by the system itself or even the flow of the helium. So it's a very low flow. We're talking about 5 liters per minute. And so we as well, to make sure, we measured with the interferometry, and with a frame rate of 10 kilohertz, these are the deviations that we obtain. So 10 in the y direction and 20 nanometers in the horizontal direction. So that's 1 sigma. And we could characterize as well overnight the drift, which is absolutely negligible for the experiment we are talking about. Because this is a strong requirement for biology imaging, we have a lab as well. We are equipped with all tools necessary for cryopreparation of samples, from the plunge freezing, microtome cryostat, and laser microdissection, which enables to shape basically samples to the proper size to be deposited on silicon nitrogen membranes. Okay, so this is about the imaging. This is the very first result, first experiment that we performed on trying to combine SAXS, WAXS, and XPCS. In this example, we are studying zeolites. So zeolites are aluminosilicates. They form at high temperature and high pressure. So this is why we had to develop this hydrothermal cell. So this is this type of studies have been going on, but there's still a strong lack of understanding of how these materials are forming. These materials are used in a wide type of applications, from catalysis in medicine, and so the understanding the formation of these materials is highly important. In this system, so we insert the gel into the cell. We heat to 100 degrees. It's all completely locked. And then we could collect this very first set of time-resolved small angle scattering. The wax was collected with the Pilates detector over here, and we could perform. So that's the work of the postdoc. He was applying Monte Carlo methods to analyze the data, and basically what he could fit and simulate is this formation, formation of from the very small initial particles through evolution of the populations. And they all correspond as well to, if you look in the diffraction data, you start with an amorphous gel that starts crystallizing into so-called LTA topology of the zeolite, that then start vanishing at the expense of another phase topology, that is the sodalite. So we are trying to disentangle and understand the mechanisms happening over here, but as well, but this is to be taken with care. These are very, very first experiment as well. So this is 1 second time framing over 2 hours, so the same reaction. And this is the 2-time autocorrelation function plot over here, collected at Q, 210 to the -3. And basically you see that along this reaction, you see really free zones. Over here, nothing is happening, everything is perfectly correlated. Over here, you have a first zone that shows that the dynamics are slowing down. It seems to be corresponding to the crystallization. And over here would be really the crystal growth. So these are very, very first results. We have to repeat to make sure that we don't have any radiation damage, or that this is accurate. So we will repeat these experiments, but this is already highly promising. This is an example, a typical example of latex particles collected the largest sample to detector distance. So you see this pattern over here that can be perfectly fitted over here. There is a bit of smearing effect that was demonstrated by a recent paper as well. And very first imaging results. So all these experiments are, because we don't have the monochromata, performed with the ping beam. So when we work at 10 keV, we have about 1% bandwidth. So it's directly coming from the undulator source. And at 4 keV, we have about 2% bandwidth. So this is the spectrum that we use. These are very first Siemens star measurements that we performed. Obviously, you have to calibrate your experiment. So this is what we did. And then the very first results. So this is as well zeolite cubes that are what we use in catalysis. So we have a large program of zeolite studies. This was the very first 3-dimensional imaging that we performed. And this is much more interesting as well. So this is a typical hierarchical sample. This is a polymer, polyvinyl sample. And interestingly, these are used for water purification. So they are membranes. They are used in catalysis as well. And it's important to be able to measure such a representative volume. So we are talking over here of a sample that is about 30 by 30 by 30 microns. We could reach resolution close to, let's say, 50 nanometers, so 33 nanometers defined by Fourier shell correlation, but slightly more than that. And if you perform segmentation, then you can really extract quantitative information about the pore networks, the size of the pores, the size of the walls, the connectivity between the different networks. And this is extremely important to be able to model then mass transport and all the phenomena that happen during the catalysis. So this is another example, slightly different polymer. This is collaboration with KAUST in Saudi Arabia. So you see this 3D rendering. And over here, when you do the segmentation, in all those different colors, basically what you identify is all the pore network. So they are all independent. So this is truly important. And then this data can be used for simulation indeed of mass transport, liquid flows, and diffusion. And to finish, I'd like to show you as well this interesting example. That is a perfect example to illustrate how large coherent beam can benefit imaging, but as well all those measurements, because radiation damage is truly an issue. And so the larger you can have your beam, the better you can be able to mitigate the radiation damage. Not only this, you'll be able to measure faster and larger field of view. So this is a pollen taken from this passion fruit that is endemic in Brazil. So you have lots of different of them. And this is the field of view over here is 60 by 60 microns. So this is very large. And we could image this object within 4 hours of measurements. And over here, you have the electron microscopy that corresponds. So this is very new. The next step, of course, is to do the segmentation. I've seen preliminary results. You can already distinguish inside the two nucleus, which are characteristic of this plant. So this is the last example that I wanted to share with you. And yes, we are open to users, so so-called user-friendly users, but in fact, it's now open to everybody. The program of user support is reinitiated as of this week. So you basically connect to SAO Online, and so there is the website over here, saonline.lnls.br. You create an account, and then it's the usual proposal application that is then reviewed by an external committee. And we have 2 calls per year, except that nowadays, because these are all new and we're still in commissioning operation phase, it's on the flow. So there is no deadline for now. And when everything will be, I guess, more stable, then we'll start again the 2 deadlines per year. And before finishing, I would like to advertise the SAXS conference, which I'm sure you're all aware. So the conference is going to happen this September. So it has been postponed by a year because of what everybody knows. So it's going to be in Campinas. The situation over here in São Paulo state is getting very much better. Brazil as a whole as well, but São Paulo indeed better. The registration is open. I don't know if you received our emails 2 days ago. So registration is open. So I invite you to go and connect. We are using the ConfTool system to do registration. It's extremely easy. So, well, you're all invited, of course, to apply. There is as well, think about your colleagues, the Guinea Prize nomination until the end of April. SAXS 2027, I don't know if someone wants to make a bid or propose to host a conference, that would be welcome as well. We do already have student funds. So if you want to make publicity to your students, if you need, we would probably pay for accommodation and reduce conference fees. And we're going to try to zero the conference fees for those who need. We are waiting for the IUCR application. We've been applying to IUCR as well for help for students. And it's likely, we are working very hard on this, to have a special issue of Journal of Applied Crystallography, potentially open access as well for the conference. So these are all the last news. Preliminary program. The thing is, we're going to have the conference in hybrid mode. Due to the situation, we had no choice. In fact, it's good as well. It's kind of a headache to organize, but it's good. It should give the opportunity to more people to participate, and maybe to expand the SAXS around the different communities. So we've tried to build some kind of preliminary program. So I'm sharing with you. I didn't put on the website yet. And the idea is to try to concentrate a bit different. So it's a bit of a different format, but the idea is to try to match as much as we can. So America, so North America, South America, of course, and Europe. Everybody would be able to attend at reasonable times. So Chicago time is over here. So for example, the first plenary for Chicago time would be 8 o'clock in the morning. It's going to be a bit more complicated for the West Coast. And Europe as well would be right in the afternoon. So this is what we are trying to do, post the sessions beginning and end of the days. We have 7 speakers, plenary speakers, they all confirmed. And so we are now just working even more on the fundings. The conference would be held in the convention center. So it's about 30 minutes, 40 minutes from the Synchrotron. So the Synchrotron is over here. You can see around, this is a very quiet place where we have the lab. It's a small city called Barão Geraldo. In fact, it's a district of Campinas. It's very quiet. It's a university small town because we have this big Unicamp University of Campinas. So it's kind of a student life. 40 minutes away, you have the convention center with accommodation. You even have a resort over here. And the conference will be held over here. The conference center is about 30 minutes away from the Campinas International Airport, which in fact, if you look in to book a flight, it's called the Viracopos São Paulo Airport, because it's only 80 kilometers away from São Paulo. So we are very close to São Paulo International Airport as well. And so being so close to the airport as well puts you 40 minutes away from Rio. So if you wish to spend some days before or after, Ouro Preto is a bit further away, 2 hours ago. And then you have the Iguaçu Falls, 2 hours flight as well. So we are close to all those famous, lovely tourism places as well. And if you're lucky, you will meet the toucan that we have actually all over the place over here. So to finish, I would like to thank you again for the invitation. Was very pleased to present the results of the concerning small angle scattering at Sirius. I'd like to obviously thank all the support groups. This is my team over here. Carla is a biologist. Aline is a chemist and physicist. We have a master student, Lais. Myself over here. Paolo is doing postdoc with me. Thiago and João are the beamline technicians. And we have one more postdoc and one PhD position open on the FAPESP grant. So thank you very much. And thank you for your attention.